Question 9. We are given a planet R. A planet has a radius R which is x by 10, where x is the radius of the Earth, RE. It's generally more commonly denoted by RE. And the same mass density. Scientists dig a well of depth R by 5 in it. So this is the planet of radius R. You dig a well of depth R by 5 and lower a wire of the same length and of linear mass density 10 to the power 3 into it. So you basically replace this area by a wire. And if the wire is not touching anything, the force applied at the top of the wire by the person holding it is, so we need to find out the force applied on this wire. So somebody will be holding it at the top by a force F, because that will need to compensate for the gravitational attraction of this wire, right? So this F will be equal to the gravitational force felt by this wire, which we can find out quite easily. We can just assume a spherical shell of radius small r and thickness dr, and we can calculate the force on this material due to this shell. So if we consider this element, let's call it dr, then the force on this element will be, or we just call it fr, it will be the mass of this element, that is dm, whatever the mass is, into rho, multiplied by the gravity at this point. Now the gravity at this point will consist of everything between this region, right? Not the sphere part that is outside of it, but everything that is inside it. I'll try to draw a better figure because I think that will be important. So this is r by 5. This is dr, and this whole is r. Right, so everything within this region will contribute. So this is the mass into gm by r squared. G into the mass of this part. The mass of this part will be the total mass of this planet into r cube by r cube. And this will be divided by small r squared. Right, so this is the force, and we need to put in dm as well. dm is equal to, this should have been dm, this should have been dm, and dm we will replace by rho dr. Rho is the linear mass density, dr is the length, right? And we just integrate it, but the limit goes from 4r by 5 to r, from this point to this point. This will be equal to the total F. How much is this equal to? Gm rho by r cube, this we take out, integral of r dr, 4r by 5 to r, which is r square by 2. So 2, and you have, this would be r squared. That means r squared 1 minus 4 by 5 whole squared, 16 by 25, which is 9 by 25. So we get F is equal to 9 gm rho, and this is r square, so only r is left, 50r. So this is the force, right? We need the value of this force. However, we do not know what m and r are, right? But we do know one thing: this radius is equal to x by 10, where r is the radius of the Earth. And we know the gravitational force at the Earth, or small g, which is 10 meter per second squared. So we can use that. So we know 10 is equal to g times the mass of the Earth by radius of the Earth whole squared. So the radius of the Earth is x squared. What is the mass of the Earth? The mass of the Earth will be, now I'll try to use another term, rho Earth here, right? Because this rho is the mass density of this wire. I should have used lambda here. I'll do that actually. I'll use lambda here and make this rho, because rho is generally mass density and lambda is the linear mass density, which we should have used. So x square is, x is the radius of the Earth, so x square is that square, rho into x cube, right, into 4 by 3 pi. This we know is 10. From that we can get the result. This is just x, so g capital G rho X is equal to 30 by 4 pi. Right, so this is one result we get. Now this, again we'll write M and R in terms of X and rho. So this is 9G lambda by 50. R I can write as X by 10. So X by 10, that means it's 5X. And here is the mass. The mass will be rho times R by 10 whole cube. Right, sorry, X by 10 whole cube, right, R cube. So 4 by 3 pi into R cube, which is X cube by 10. Right, so how much does this come out to be? And we'll just input the value right here. G rho X is 30 by 4 pi. So G rho, and this is X squared because 1 cancels. So we'll just leave 1X, and the G rho X that is left is 30 by 4 pi. And this cancels a lot of stuff. 3 by 4 pi cancels with this and leaves us with a 10. Right, and that 10 cancels with this 10. And what we are left with is 9 lambda by 5. You might be mistaking the 10 here. Let me just check. So, yes, M is written to be 4 by 3 pi x cube by 10. No, it should be x cube by 10 cube. Yes. So this was 10 cube. 1 10 is cancelled. We still have 100 left. So 9 lambda by 500 is the force. Into x, right? There's still an x left. So 9 lambda by 500x is the force. That comes out to be 9 by 500 into lambda is given to us to be 10 to the power minus 3 into the radius is given to be 6 into 10 to the power 6. So this cancels with this, gives 10 to the power 3. This cancels with these two, gives 10. This cancels with this, gives 2. So we have 12 into 9. 12 into 9 is 108 Newton. So the answer is 108 Newton, which is option B. Right, I won't suggest, I know this has been a little untidy in the calculation, but you do it yourself. I've told you the exact concept. Right, the concept should be what is important. And ultimately, if you do it correctly, then you will get the answer. The force is 108 Newtons. We got this value, that was the conceptual part. And then what they did was, instead of giving us the radius and mass of this planet, they gave us the radius of this planet in terms of the radius of the Earth, telling us that they are basically made of the same material, and knowing that for the Earth, gm by r squared is equal to 10. And they gave r. So basically what they did was, they gave us r and they know when we know gm by r squared. So they said you can find out m, and then this density you'll know is the same as the density of that planet, so you can find out the other stuff as well. So sort of a lengthy question. Chances are somebody might make a mistake somewhere, but not a very difficult one conceptually.